So our next talk is a remote talk. The speaker is Oleg Kutkov. He is live now here, and he's at home in Ukraine. As most of you know, people cannot leave Ukraine because of the war conditions, and I'm very happy that Oleg can join us like this. And I would like to introduce Oleg. So he's from Kyiv. He's an embedded software developer during the day, and an embedded software developer, hardware hacker, and RF engineer at the night. And his total work experience is more than 10 years, and his fields of interest is electronics, software development, hacking, reverse engineering, signal processing, and space technology. And he's an active open software and open hardware contributor, and he loves to write technical articles in his blog, which is olegkutkov.me. So please give Oleg an applause here on the screen. Welcome, Oleg.
Hello.
Okay, then I think we can start into the talk right away. Short notice on how we're going to do that. We have also, in this case, pre-recorded the video, and Oleg and the stream, everyone is following the pre-recorded talk. We're going to play the pre-recorded talk now, and afterwards we're going to have a live discussion. So you can raise your questions directly to Oleg, and that's how we're going to do it. Okay, video team, please go ahead.
Hello, thank you for the invitation. My name is Oleg. I'm embedded system developer, and also I'm RF engineer, software and hardware hacker. And today I would like to talk about one of my current projects. It's HackRF Supercluster. For some years I interested in satellite communication and signal processing. So I started experimenting with different software-defined radio boards, and eventually I came up to the idea to build a wideband SDRA receiver to be able to monitor and analyze more signal at the same time. So yeah, this is my project, HackRF Supercluster. I call it a crazy way to build a wideband SDR because building this project involved a lot of efforts, a lot of hardware and software. I will show it in a minute. So yeah, first let's talk about bandwidth. What is bandwidth? Bandwidth is just a difference between the upper and lower frequencies on some continuous band of frequencies. That's true for any kind of electromagnetic radiation, both radio waves and visible light. For example, all eyes have a bandwidth of 4,400 nanometers. So we can see the light from blue to red. So yeah, here is bandwidth of our eyes. The same thing is in radio communication, where we can have a receiver that could receive some frequencies in some specified bandwidth. So yeah, let's talk about bandwidth in communication. Here I have some popular examples. For example, FM analog radio. One station occupies 200 kilohertz. This is the bandwidth of the single station at FM analog radio. This bandwidth requires two audio channels for stereo, one mono audio channel, plus optionally some information like traffic, weather, and so on. If we talk about analog PAL TV broadcast, the single channels occupies up to 8 megahertz. This includes video and audio, video in color. So yeah, in the case of digital communication, for example, Wi-Fi, we can see that required bandwidth is much wider. It might be 20, 40, or even 160 megahertz in the latest Wi-Fi standards. So yeah, why the bandwidth is so important? Wider bandwidth allows us to push more information, to pack more information in this range of signals. For example, you can see it's on Wi-Fi example, where the lowest bandwidth, like 20 megahertz, allow us to achieve speeds, for example, like 60 megabytes per second. And with wider bandwidth, we can achieve up to 1.3 gigabits, which is huge, actually. Sure, your data throughput depends not only the bandwidth, but also on modulation, signal level, and some other tricks like MIMO and so on. But yeah, bandwidth is really important. Here I have some more examples, like Starlink satellite constellation. Starlink uses 2,150 megahertz of bandwidth, and this gives up to 4,400 megabytes per second of download. And the last example is DVB-S2. It's satellite broadcast television, digital. One single channel occupies 30 megahertz of the bandwidth. So yeah, as you can see, the most interesting signals to receive and analyze occupies at least 8 megahertz, and if you try to receive analog TV, if it's present in your location. So yeah, let's switch to the SDR receiver. What we have now. Here are some popular receivers. Most popular is maybe RTL SDR. The maximum bandwidth of this receiver is 2.4 megahertz, and this device, this is a really low-cost device, maybe $40 US dollars or something. So yeah, as you can see, the bandwidth is quite small, so we can use it to receive FM radio stations, some old weather satellites like NOAA, and so on. And we can use it for ham radio communication to monitor ham radio signals, but not more. Another popular board is HackRF, which can give up to 20 megahertz of bandwidth, and this is good for most of the cases. We can receive analog TV, we can receive more signals from satellites, and so on. Platter SDR have the same bandwidth, and then we have Blade RF Lime SDR, which can give up 60 megahertz of bandwidth typically. But those boards are more expensive. For example, you can buy HackRF for a clone of HackRF for, I don't know, maybe $70, $80 US dollars, and Lime SDR will cost you more than $300. Sure, this board is much better in anything, but yeah, it's quite costly. And the last one is USRP from HackRF Research. This is a really great devices. It's perfect for lab usage, but it costs a lot, starting from $2,000 and up to $20,000. Yeah, this is an enormous price, but you can get up to 20 megahertz of bandwidth, so you can receive almost anything. So yeah, when I started this project, I already have had some of HackRF boards that I bought in different stage of my life. So I thought, what if I can combine bandwidth from all my boards? For example, one HackRF board could provide up to 20 megahertz of bandwidth. So yeah, two boards can give 40 megahertz, and this is great. So yeah, I decided to buy a few additional boards and started my project that I called HackRF Supercluster. Yeah, here's a HackRF1 board, original board, but I had Chinese clones, which is much cheaper. So yeah, the total cost of my receiver was smaller than the same combination, than would be the same combination of Lime SDR or any other receivers. On the initial stage, I started experiment with only 2 boards. I tried to sync these boards. You can see my original setup on the photo. This is 2 boards which synchronized by the clocking and GPIO synchronization. HackRF boards have 2 ports for the clocking. One is an external clock input, so you can fit any clock source, 10 MHz clock source to your board, and clock output, so you can drive some external device like other HackRF boards. So you can see that one board is connected, clock output of the one board is connected to the clock input of the second board. Plus, there are some additional wires. Those wires connects GPIO pins of the MCU of the board. This helps to synchronize sampling of the boards. So yeah, plus you can see on the photo my handmade RF splitter. This is just a resistor divider, very simple. Plus I installed additional clocking. This is a green board on the top HackRF. So yeah, then I started experimenting with software. I used GNU Radio for graphs for all my experiment and software. So yeah, this is how it looks like. I tried to tune to the one of the satellites, broadcast satellite signal. So here we have a full DVB-S2 broadcast spectrum. We have 40 MHz bandwidth. So yeah, the signal of the satellite is clearly visible. We can definitely tell that there is a signal, but there are some problems. As you can see, there is some notch in the middle of the spectrum. This is effect of the combination of 2 spectrums when you're using resampling filter. So yeah, you need to resample the input signal in order to combine your signal to basically a new sample rate. So yeah, we have in input we have 2 20 MHz signals, but we need to get 40 MHz signals. So we need to resample each signal up to 40 MHz and then combine them. This resampling creates some filtering, which give us this notch in the middle. So yeah, it actually ruins the signal, but it's good enough for monitoring and some initial experiments. Then I decided to go up to 8 boards. Here's you can see my setup when I started to build it. Why 8 boards? I decided that 160 theoretical bandwidth is great for most of the applications. Plus, it nicely fits with my splitters that you can see on the photo. I had 2 H-channel splitters. So yeah, that's why I decided to use 8 boards. Here's the layout of my splitters. I have 3 splitters, 2 identical PD1140 splitters with 4 channels, and additional mini circuits 2-channel splitter. Sure, the splitters create a lot of attenuation of the signal, so I'm using additional low noise amplifier in the input. It's not shown on this slide. So yeah, when you're dealing with some USB devices, you might have a bandwidth problem of your you may find a bandwidth problem of your PC and your USB bus. In typical computer architecture, USB ports that's available to users are connected to some USB hub, and then this hub connects to the USB host controller and to the CPU. But in this case, you can't use both these ports for a full bandwidth because you know, two ports are connected eventually to the single port of the USB 2.0 or 3.0, and here's your bottleneck, your limitation. One HackRF boards at 20 megahertz bandwidth generate up to 320 megabits per second, megabits per second of the data, and this is almost saturate single USB 2.0 link, which is 400 megabits per second. So yeah, to solve this problem, I decided to use separate USB host controllers for each board. So yeah, I came up to the something like this that you can see on my slide. Here is we have 8 HackRF boards, 8 USB host controllers, which is USB to PCI X1 controllers, and all those boards are connected to PCI riser card, which is typically used to connect the graphics adapter, and then all this data is combined to PCI link, which is connected directly to the CPU. The bandwidth of the PCI link is enough to work with bandwidth of all 8 boards. So yeah, this is a good solution. And I built maybe most wide-looking PC or data acquisition station. Here you can see all the 8 USB PCI controllers that are connected to the PCI riser card. Yeah, here's the card. Here's my card. I actually found it on eBay, and for some reason this card is quite rare. I know that such type of card are used by miners for Bitcoin, Ethereum, and so on. So yeah, maybe you can still find this board. This board is sits in the PCI Express 0 channel, which is typically designed for video card graphics adapter, because this slot has a direct connection to the CPU. Any other PCI slots might be connected to the CPU via hub or some additional chipset, which is not great for this application. Another important question is clocking and synchronization. On my first initial setup, I mentioned about clocking. So yeah, on my first setup, first HackRF boards clocks the second HackRF boards. It's very important to synchronize the boards so all the boards could work as one board, so they can sample at the same time. Sure, you can always connect one board to another board to a third one, and so on. But this creates a big problem because on board PLL chip is not perfect, and each connection creates additional delay between. So the clock signal that enters the first board will differ from the signal that enters the last board. It will differ by phase, plus there will be additional phase noise, some instability, and so on. So yeah, this will ruin the whole setup. That's why I decided to create a special clock distribution amplifier. Here you can see my boards. I will show it now. So yeah, this is a 8-channel clock distribution plus 8-channel 1 PPS distribution signal. This board is connected to my GPS DO. This is just GPS disciplined oscillator that creates 10 megahertz square signal plus 1 PPS or 1 hertz signal. You can see the delay lines on the photo. These lines use it to match all the outputs. So all eight outputs will have the signal that perfectly in phase. So you can feed all the 8 HackRF boards with the same clocking signal that without any phase problems. 1 PPS signal is used to sync sampling of each board. So basically, all the boards start sampling of the on ADC at the same time, almost on the same time. For the 1 PPS signal, I used additional buffer IC. You can see it on the photo. It's U4. So yeah. When I designed this board, I made some experiments with my logic analyzer, and I found that all the signals, 1 PPS and 10 megahertz clocks, are perfectly in phase. Timing resolution of my logic analyzer is 1 nanosecond, and I can't find any phase difference in this business domain. So yeah, it might be some difference, but it's less than 1 nanosecond, and I think it's great. I built an enclosure for my board. Here how it looks inside, and here's how it looks outside. Front panel on the top photo, and bottom panel, and all outputs you can see on the second photo. It's clock output and 1 PPS output. And here's the final construction. I had to build all the cables for the 1 PPS and clocking signal. Those cables are match in length, so there is no any additional delays or phase inaccuracy. So yeah, I made a lot of measurements and it's worked great. You can see the clock distribution box under my HackRF cluster, plus all the splitters, plus 2 low noise amplifiers and additional high pass filters. It's a blue high filter. It's a blue cylinder. On this photo, the setup is connected to the satellite antenna, so I can monitor satellite signal. The antenna is connected using bias T. It's a metal box on the right down corner. Plus, you can see a very special board in the middle of the photo. On the bottom, it's red board. This is another my project, satellite LNB controller. This board is used to control satellite down converter. It generates different voltages, different control signals, and it's controlled via USB using special tools, which has a really nice user interface. So yeah, but this is another story. So yeah, the first revision of the software was totally the GNU radio flow graph. You can see it on the screen. I used Osmocom source to get the signal from the old boards. Plus, I had to patch this block additionally. So now I can use 1 PPS synchronization. Basically, I had to add calling of the one function, which enables synchronization on all boards. Then there is some protection like IQ correction. sampling from 20 megahertz to 160 megahertz, and then multipliers. And the output it might be some file sync or GUI sync, which shows the spectrum. Plus, there are a lot of controls, so I can control receiver frequency and bandwidth and some additional params like spectrum's intersection. So it might help to clear that notch that I mentioned in the beginning. So here's the user interface of my flow graph. You can clearly see two spectrums and part of the third spectrum on the waterfall display. Controls allows to set central frequency, gain, plus overlap for the spectrums. And here's some results. Here's 160 megahertz bandwidth of the satellite signal. And you can see, you can clearly see two signal of two DVB-S transponders. It's on SDRA'22 satellites. Plus, there are two additional signals, but I could not identify those signals. Also, you can see the gap between spectrums. So yeah, this is a problem that I already mentioned, and I will talk about it more. Plus, currently I'm running additional software, which is a multi-channel receiver or a multi-channel monitoring tool. Here is the current user interface. Basically, it's combination of 8 individual receiver in one window. So you can tune each receiver at any individual frequency. You can set any required bandwidth and some other params, and you can monitor and see all 8 receivers at the same time. This might be useful for some data acquisition and monitoring tasks. For example, you have 8 transmitting channels, but you don't know when all the channels are transmitting and so on. So you can use this tool to monitor all these channels and see how your source is transmitting something at each individual frequency. In my experiments, I used this tool to monitor Starlink user terminal transmission, because Starlink uses 8 channel for upload. It's a Ka band. So I used the whole my setup, including low noise block, LNB controller, and so on. Using this tool, I am able to see the channel distribution that is user terminal using. So yeah, this is great and fun. What's about signal demodulation? Is it possible to demodulate the receiving signal, wideband receiving signal? Unfortunately, it's not at this point, because what we have, even when we synchronizing all these boards with the same clock signal, when we have 1 ppm synchronization, it's anyway didn't help us to solve a phase noise problem of the HackRF PLL chip and HackRF mixers. Yeah, all signal will be in some kind of phase, but at the same time there will be phase instability, and this phase instability will be unique for each board. How we can solve this problem? I'm thinking about introducing some reference signal. So maybe I can fit some stable reference signal at the input of the boards. So on the software side, I will be able to adjust phases basing on this reference signal. I did not try it yet, so yeah, this is just a speculation. I hope it will work. Plus, we have this gap between spectrums that happens due to resampling. At this point, I don't know how to properly solve this problem, but I am looking for a solution because I started signal processing not so long ago. So yeah, it might be that I just don't know something about signal processing. So yeah, I'm doing my research. Plus, there might be some improvements in scheduling and data acquisition from the computer side. Yes, I'm using individual PCA lines and USB host controllers for each board, but data acquisition might be affected by operating system scheduler. So I think that I will try to isolate 8 CPU cores on my computer to perform just data polling. For example, core 0 of my CPU will work just with the first HackRF board, second core with the second board, and so on, without any interruptions and so on. I hope that this will help to improve performance and accuracy of the data acquisition. But yeah, anyway, with all these problems, it's still usable for signal monitoring, and also you can demodulate some individual signals that fits bandwidth of the single HackRF boards. So yeah, it's still usable. Plus, it's very fun to build. I do believe that one of the best way to learn something is to try to build something with your hand or with your knowledge. So yeah, this was very interesting. I learned a lot of new things, and I'm still learning. So yeah, I think this is a great and fun project. And I think that's all. Here you can see some links on my website, on my Twitter, and on my GitHub. So you can find everything about my supercluster, all the schematics, all the source code, and so on my blog for both HackRF Supercluster, clock distribution boards, satellite LNB controller, and so on. So yeah, you can visit my pages to check this out. So yeah, I think that's all, and thank you.
Okay, Oleg, thank you very much. Now Oleg is live again.
Hello?
Yes, we can hear you. Okay, we have a very short time slot for 1 or 2 questions. So, are there questions from the audience?
Yes, about the problem with the phase noise of the mixers of the HackRF. Is it possible to have a kind of comp source and actually with the low noise phase noise input that actually has a proper low and phase noise spectrum on each of the inputs of the PLLs? Or is that not the right way to approach that?
Actually, I have some updates. I made some additional experiments and wrote some new software. So I tested the phase instability of each board, and actually I found that the problem is not so big that I'd imagined. I found that 3 boards are just in phase, already in phase, and all other boards phase difference is something around 6 milliseconds. And also I managed to compensate all these phase delays. I'm compensated manually currently with my stable reference signal at the input. But yeah, I believe it's possible to compensate automatically. So yeah, I think it will work.
Okay, one last question, please.
Oleg, I want to ask you, did you notice any problem of the analog digital converter in receive mode, as it has only a resolution of 8-bit to my knowledge? Maybe it's a better version you have. Did you notice any problems of this 8-bit conversion?
No, at this point, no.
Okay, thank you very much.
Thank you.
Right, then we're at the end of the time for this slot. Oleg, thank you very much. And I'm happy that you were able to join us from Kyiv, from Ukraine.
Thank you for having me.
Thank you, Oleg.